All right, this is AP Physics C on February 25th, 2021. So basically, it's the repeat lecture on how to deal with elliptical orbits. Before, when life was simple, we had circular orbits. And there would be something like a central body with radius capital R that represents the distance to the surface from the center of that central body. Then there's the orbit radius, lowercase r, and separately, there's the altitude h of this object above the surface of the central body. So we have the orbit radius lowercase r is equal to the radius of the central body, such as the Earth, plus the altitude above the Earth. These two distances add together equal that distance. And then we had all of our fun equations, such as the orbital speed in a circular orbit. So this is for a circular orbit, is equal to the square root of g times m divided by the orbit radius. And Newton's version of Kepler's third law, we could say the period squared is the product of 4 pi squared r cubed divided by g divided by m. A little cautionary reminder, g, of course, is the universal gravitational constant. The period has to be in units of seconds, and the radius has to be in units of meters before you can plug them into this equation and do your work. So now we're going to get advanced and deal with elliptical orbits. Imagine that I drew an ellipse here. So it was discovered by Johannes Kepler that Mars is not in a circular orbit around the sun. And from that, he developed his 3 laws of motion that deal with elliptical orbits. So first of all, on an elliptical orbit, here's the long axis, here's the short axis. This short axis is called the minor axis. And half of the length of the minor axis is represented by the variable lowercase letter b. The long axis is called the major axis. And half the length of the major axis is called lowercase letter a, the semi-major axis, the distance from the center of the ellipse to the farthest point away from the center on the ellipse. And what Kepler figured out is that Mars is on an elliptical orbit around the sun, and the sun is not in the middle of this ellipse. There's 2 other points that we care about in an ellipse. They're called the focal points. So one is here, and the other is the equal distance on the other side. Let's say it's there. The more elliptical this is, the farther the focal points are apart from each other. And there's some variable letter c, and I forget where it is geometrically. It might be from here to there or from here to there. Whatever it is, there's some variable c as well that we don't care about at the moment. What Kepler figured out is that the sun, or in this case, the central body, is at one of the 2 focal points, and there's nothing at the other focal point. Okay, so if this were Mars and that's the sun, great. There's a couple of terms that you might as well learn right now. The point in the orbit, and by the way, most objects in the universe are, all objects in the universe that are undergoing motion just to universal gravitation are in conic orbits. So that means they could be a perfect circle, which really doesn't occur in nature. There are no perfectly circular orbits that I know of. This is an elliptical orbit, elliptical, and everything that's in the solar system that is bound to the solar system is in an elliptical orbit. So all the planets going around the sun, the moon going around the Earth, the asteroids and the comets in our solar system are all on elliptical orbits. As far as conic sections go, you can have circular orbits, you can have elliptical orbits, you can also have parabolic orbits. Comets occasionally come in on parabolic orbits, meaning they come in from infinitely far away and they go whizzing around their sun and then they go away off to infinity. And very, very rarely, we even get hyperbolic comets shooting through our solar system, where that means not only did they go to infinity, but when they got to infinity, they were still going with positive kinetic energy. Okay, so in other words, it's as if they were thrown into our solar system from infinitely far away. Very rarely we do see comets whizzing through on hyperbolic orbits. And as a fun fact, there's a guy who recently studied the motion of a comet that passed through our solar system in 2017, and he claims it wasn't on any of these conic sections, and therefore we were visited by space aliens on a ship that was maneuvering and thrusting as it passed by. Keep in mind that comets do emit gas and dust as they get heated up by the sun, and so that can cause them to have non-conic behavior because there's thrusting as these gases push the comet around. So, don't know. Jury's still out. Back to today's exciting new equation. A term for you to learn right now is a name for the shortest distance from the center of the central body to an object orbiting it on an elliptical orbit. That shortest distance is named the Periapsis Distance. Periapsis. So periapsis is Periapsis, and it means closest point in an orbit to the central body. When the central body happens to be the sun, then we call this perihelion, from helios meaning sun. Helium, the element, is also named after Helios, the sun. So closest to sun. If it happens to be the Earth, we call it perigeo, Earth. If it happens to be the Moon, we call it peralune, meaning closest point in its orbit to the Moon. And I think they have one for Mars. We don't care. The generic term that we can just use always is periapsis, closest point in the orbit. Well, by the laws of physics, and what Kepler realized is that the closer you are to the central body, the faster you're traveling at that point. So V sub P is the term that we'll use for periapsis velocity. And as I hope to show you in this session, there's an equation to calculate it. There's also a name for the farthest distance in an orbit from a central body. That farthest distance is called apoapsis. So apoapsis means farthest point in an orbit from a central body. And just like perihelion means closest to the sun, apohelion means farthest from the sun. Perigee, closest to the Earth. Apogee, farthest from the Earth. Paralune, closest to the Moon. Apolune, farthest from the Moon. There, you learned some Greek. But wait, there's more. The farther away you are from the central body, the slower you're traveling. It's like you had to go uphill out of the gravitational well, and you slow down as you go up. So here, the velocity at apoapsis is your speed at the farthest point in your orbit from the central body. So v lowercase a is your apoapsis velocity. Oh man. Well, there's a way to calculate your speeds, your orbital periods, when dealing with elliptical orbits. And the good news is, once you've learned how to do circular orbits, then you can bring that knowledge to bear in dealing with elliptical orbits. So a reminder, if I had a circular orbit of radius r, my speed would be square root of gm over the orbit radius. The orbital period squared would be 4 pi squared times the orbital radius cubed divided by the universal gravitational constant divided by the mass of the central body. Great. Now, bringing that to bear for an elliptical orbit, the good news is the average speed and the period of an elliptical orbit is the same as the speed and period for a circular orbit whose radius is the average of the elliptical orbit. Oh man, how do I get that? Why, look, children, if I take the distance of periapsis distance, r sub p, and I add to that the distance to apoapsis, r sub a for apo, then the total distance from here to there is the major axis. That is A and A. A gets us halfway across, A takes us the other way across. So A is the semi-major axis. So 2A is equal to the periapsis distance plus the apoapsis distance. So if I want to solve for the apoapsis distance, A, that is just the average of the periapsis distance and the apoapsis distance. Ta-da! That means life is good for us. Life is simple. Life is manageable. Life is basic orbital mechanics. So let's do an example of calculating your average speed and average orbital radius. So an example. Suppose I'm orbiting the Earth and I am at a closest point to the Earth of, I'll do 10,000 kilometers again, like I did last period. But this time I'll say my apoapsis distance, let's say it's 50,000 kilometers, just to have a different example. Why, then my semi-major axis would be 10 plus 50 is 60. 60 divided by 2 is 30. So my average orbital radius, my semi-major axis for this elliptical orbit, would be 30,000 kilometers. If I think of this as being a circular orbit of radius r, using a for r, then I would say my average orbital speed is the square root of gm over this semi-major axis. And the period squared would be 4 pi squared times this semi-major axis cubed divided by g divided by the mass of the central body. Note A is not acceleration the way it's been throughout the entire school year. A is semi-major axis. All right. How much fun is that? So that's how you find the average speed of an object in an elliptical orbit. But wait, there's more. We need to be able to calculate the speed at perigee or periapsis, the speed at apoapsis. To get them, there's a handy dandy formula for each one. Here it is. To calculate the speed at periapsis, multiply the average speed, which you get from here, by the square root of the ratio of the apoapsis radius divided by the periapsis radius. The big number over the little number, square root, because this is a faster speed than average. To calculate the apoapsis velocity, you multiply the average speed by the flipped ratio, the ratio of the periapsis velocity or radius over the apoapsis radius. In other words, instead of multiplying by this top ratio, you're dividing by this top ratio. All right, so putting some numbers into this example, I have conveniently written a program that does this sort of stuff for me. And I've called my program Orbit. So we will trust my programming skills to verify that we're getting the same results, whether we do it as a circular, average, or elliptical in this case. So let's set our central body equal to the Earth. Let's do the circular orbit first and say that its orbital radius is the average of 10,000 and 50,000 kilometers, in other words, 30,000 kilometers. Okay, so 30,000 kilometers. And as you no doubt would have calculated by hand, that means its altitude above the surface of the Earth, h, is equal to the orbit radius minus the radius of the planet, is 23,622 kilometers. And the stuff that I'm going to say is proof is the circular r equals 30,000 kilometers. In that case, the period was 23,622 seconds, and my orbital speed was 3,645 meters per second. Okay, so here I just wrote a program that does what you do by hand. And I conveniently also express it in minutes and hours because I want to know. So now, what about this elliptical orbit? And as you can see, there's more for you to learn after you learn about elliptical orbits. So this elliptical orbit, I'm going to put in the two radii. Its periapsis radii was 10,000 kilometers. Its apoapsis radii was 50,000 kilometers. So when you get done plugging it in, here's what you get. You would say in this elliptical orbit, the semi-major axis. So what does all this say? Here's my periapsis radius, my periapsis altitude above the surface of the Earth. My semi-major axis is 30,000 kilometers. My apoapsis radius is 50,000 kilometers. My apoapsis altitude is the radius minus the radius of the Earth, 42,622 kilometers. And there's the period. Oh, I see. Yeah, no. The period is not matching, is it? Interesting. It says the period is 51,713 seconds, and my average speed is 3,645 meters per second. It also says my periapsis velocity is 8,151 meters per second, and my apoapsis velocity is 1,630 meters per second. And what troubles me is it says the period is 51,713 seconds, and that means I wrote down the wrong number for the period for the circular orbit, didn't I? So let's go back and do that circular orbit calculation again, and this time put in the right number, 30,000. Oh, so I wrote down the altitude when I was supposed to write down the period. The altitude was 22,622. The period was 51,713 seconds. So 51,713 seconds. And my claim is, oh, look, for the circular orbit, the period matches the elliptical orbit. The average velocity matches the average velocity. And now I'm going to get out of this. We don't need this anymore. Quit. How do I calculate, or how do I prove to you that these equations are correct? The answer is take this average velocity from the circular orbit, 3,645 meters per second, and multiply it by the square root of 5. Because 50,000 over 10,000 is 5 over 1, so this is just the square root of 5. If you go 3,645 times the square root of 5, whoop, sure enough, it says 8,150.5 compared to the 8,151. So I'm claiming they match, 8,150 meters per second. And this one is the average speed, 3,645 meters per second, really divided by the square root of 5, which is the same thing as inverting and multiplying this term here. So if I go 3,645 divide by square root 5, enter, sure enough, I get 1,630 meters per second, in agreement with the fancy formula there. Or you could say, I wrote the program to match the formula correctly. I correctly wrote the program to match the formula. Okay, so that's the new skill for you to become masters of. Anytime that we have an elliptical orbit, now, yikes. Anytime that we have an elliptical orbit, the periapsis radius is equal to the radius of the planet plus the periapsis altitude. The apoapsis orbital radius is equal to the radius of the planet plus the apoapsis altitude. The semi-major axis is the average of the periapsis and apoapsis radii. The period of time is 4 pi squared semi-major axis cubed over gm. The average orbital speed is square root of gm over the semi-major axis. Periapsis velocity is equal to the average speed times the square root of r apo over r peri, and apoapsis speed is the average orbital speed times the square root of r peri over r apo. Ta-da! Everything you ever wanted to know, scribbled down on one small piece of paper.